Now, prepare for your mind to be stretched and space itself to be bent. In today's episode of A Brief History of Mathematics, Professor Marcus de Sautoy tells the story of the mathematicians who helped Einstein with his maths. Without their stunning mathematical insight, Einstein's theory of relativity just wouldn't add up. Here's Marcus de Sautoy.
Albert Einstein is a celebrated genius. Everyone is familiar with his picture. His theory of relativity is famous. But without the ideas of three pioneering mathematicians, Einstein's relativity just doesn't work. In this brief history of mathematics so far, I've shown time and again how mathematics is the key to understanding the physical universe. As Galileo once said, without the beacon of light that mathematics provides, we would be wandering around in a dark labyrinth. The mathematical pioneers in today's episode provided Einstein with a map to navigate the darkest labyrinth of all, the fabric of the universe. Janusz Bolyai, Nicolas Lobachevsky and Bernhard Riemann, these three extraordinarily bold mathematicians created weird new geometries that took us into strange, bendy worlds. They were motivated by mathematics alone. But the new geometries that they created in the 19th century form the backbone of one of the greatest achievements in 20th century physics. Be warned, these strange new geometries created by Riemann and the others are not so easy to understand, even for the genius Einstein. Theoretical physicist Roger Penrose.
Einstein was a good intuitive mathematician, but he wasn't a sort of scholar in mathematics, and he had a bit of trouble with some of these ideas. But he knew what he wanted, and when he saw what Riemann had done, this was it.
Bernhard Riemann's mathematics gave Einstein the insight he needed to develop his theory of relativity, even if he did find the mathematics a little tricky.
A Brief History of Mathematics with Marcus de Sautoy.
For 2,000 years, the axioms enshrined in Euclid's great work of geometry, the Elements, were accepted as absolute and unquestionable mathematical truths. But in the mid-19th century in Europe, there was growing unease about some of Euclid's ideas. Mathematicians started to question whether there might be other sorts of geometry out there, geometries that Euclid hadn't described, geometries in which, a radical thought, Euclid's axioms might be false. It's hard to overstate just how radical this suggestion was. In fact, it was so radical that one of the first mathematicians to entertain such an idea, Carl Friedrich Gauss, was reluctant to talk about it, even though at the time he had near godlike status in the mathematical world, and a flawless reputation. He could have said almost anything, and most mathematicians would have believed him. But Gauss kept quiet, not mentioning to a soul his radical suggestion that space itself might be warped. Meantime, in Transylvania, another mathematician, Farkas Bolyai, was thinking along similar strange new lines, contemplating mathematical scenarios where Euclid's geometry might be false. Farkas Bolyai had cut his mathematical teeth alongside Gauss in the University of Göttingen. He'd spent years wrestling unsuccessfully with the possibility of new non-Euclidean geometries. The effort had almost crushed him.
I have travelled past all the reefs of this infernal Dead Sea, and have always come back with broken mast and torn sail. The ruin of my disposition and my fall date to this time. I thoughtlessly risked all my life and happiness.
In 1823, he received a letter from his son, also a mathematician, who was stationed with his army unit in Temesvar.
My dearest father, I have so many things to write to you about my new discoveries that I cannot solve it in another way than doing nothing else than writing you this letter, without waiting for your answer to my previous letter, and perhaps I shouldn't write to you before getting it. But I have found beautiful things that surprised even me, and it would be a pity to lose them. My dearest father will see and know, I cannot say more, only that from nothing I have created a strange new world.
Farkas's son Janos had discovered what he called imaginary worlds, mathematical worlds that didn't satisfy Euclid's axioms, yet seemed to be entirely consistent and without contradictions. His father wrote immediately to his hero Gauss about the exciting discoveries that his son had made. Gauss wrote to a colleague praising the brilliance of this young mathematician.
I will add that I have recently received from Hungary a little paper on non-Euclidean geometry. The writer is a very young Austrian officer, the son of one of my early friends. I consider the young mathematician J. Bolyai a genius of the first rank.
But in a letter back to his father, Farkas Bolyai, Gauss had some bad news.
If I commenced by saying that I am unable to praise this work, you would certainly be surprised for a moment. But I cannot say otherwise. To praise it would be to praise myself. Indeed, the whole contents of the work, and the path taken by your son, coincide almost entirely with my meditations, which have occupied my mind partly for the last 30 or 35 years.
Janos was completely disheartened. His father tried to console him.
Certain things just have their epoch, when they are found at different places. Just as in spring, when violets come into the light everywhere.
Despite his father encouraging him to publish, Janos Bolyai didn't write up his ideas until some years later. It was too late. In yet another body blow, Janos discovered that the Russian mathematician Nicholas Lobachevsky had published some very similar ideas 2 years before him. The radical geometries of Bolyai and Lobachevsky were confined to our three-dimensional universe. But one of Gauss's students at the University of Göttingen took these strange new geometries in an even more exotic direction. Bernhard Riemann was a shy and brilliant mathematician. One of his contemporaries, Richard Dedekind, wrote of him,
Riemann is now very unhappy. His solitary life, and in addition, his physical suffering, have made him extremely hypochondriac and mistrustful of other people and of himself. He has done the strangest things here only because he believes that nobody can bear him.
But in his solitude, Riemann was exploring the contours of strange new worlds he had constructed. In the summer of 1854, Riemann faced one final hurdle before he could become a professor at the University of Göttingen. And given his introvert nature, it was quite a hurdle. He had to give a public lecture to the philosophy faculty on the hypotheses which lie at the foundations of geometry. And so it was that Riemann found himself having to present the incredible ideas that he'd been formulating about the nature of geometry. He fretted dreadfully. He hadn't expected the faculty to choose that topic. He hadn't completely finished every detail of his theory. But if he wanted his professorship, there was no way out. With the benefit of hindsight, it's tempting to say, thank goodness for that. On the 10th of June 1854, Riemann delivered his lecture. Gauss was in the audience. He showed the mathematicians sitting in the Göttingen lecture theatre how to see in 4 dimensions and beyond. He described shapes that could only be seen in the mathematician's mind's eye, and made them as tangible to the mathematicians listening as the 3-dimensional benches they were sitting on.
Gauss was impressed. It was pretty hard to impress Gauss, and he really was impressed by what Riemann had done. So Riemann showed how you could build up what we would call non-Euclidean geometry, because there are a lot of assumptions in Euclidean geometry, basically that things are the same wherever you are. I mean, there's a lot of symmetry. If you draw a square over here, it's the same as a square over there, you see. And you can move things around within the geometry. The more general kind of geometry is where your bendiness can change from place to place. And this was the kind that Riemann developed. Riemann started off this idea of n-dimensional curved space geometry.
Riemann's theory of n-dimensional curved space pushed mathematicians out of our 3-dimensional universe and took them in a completely new direction. His new theory of geometry allowed them to move from 3 dimensions into 4 dimensions, 5 dimensions, 6, 7, even n dimensions.
If you're not a mathematician, I reckon this is about as close as you can get to experiencing the 4th dimension. I'm standing under La Grande Arche at La Défense in Paris, designed by architect Johann Otto von Spreckelsen. What he's done here is to build a shadow of a four-dimensional cube at the heart of three-dimensional Paris. It's an absolutely staggering structure. You can fit the towers of Notre Dame through the arch. But it's the power of the idea that it represents that is even more staggering. How do you represent a 4D cube? Well, the best way to understand this is to think how an artist working on a two-dimensional canvas can draw a three-dimensional cube. One way they might do this is to draw a large square with a smaller square inside, and then by joining up the edges, you suddenly get a sense of depth in the canvas. The architect here at La Défense has done the same thing, but one dimension higher. He's built a smaller cube inside a larger cube, and then joined the corners of the cube up. And voila, a shadow of a four-dimensional cube sitting at the heart of Paris.
The hypercube in Paris is a wonderful way to get a taste of another dimension. But if you really want to understand life in anything more than 3 dimensions, it's Riemann's revolutionary mathematics that you need. 50 years after Riemann's famous 1854 lecture, his radical mathematical ideas came into their own. The physicist Albert Einstein was contemplating the fabric of space when he came across the mathematics of Riemann. Theoretical physicist Roger Penrose.
At first, he didn't like it. He thought, oh, you mathematicians make this life so complicated, you see. And then a little later on, he came around and realized this was the way to look at it. And it was absolutely crucial, because this four-dimensional geometry, 1 dimension of time and 3 dimensions of space, all fit together into this beautiful kind of geometry. Einstein could see you could generalize that in the way that Riemann generalized Euclidean geometry. You can have Euclidean geometry in n dimensions, you see, but then the real generalization is to make it curved, and that's what Riemann did.
Using Riemann's mathematics, Einstein was able to make his extraordinary breakthrough into the nature of the universe. Time, he realized, was the 4th dimension. Riemann's new geometry enabled him to unify space and time. And the strange curved geometries that Gauss first thought about, Bolyai and Lobachevsky described, and Riemann generalized, helped him to sort out relativity. If you try to measure the distance between 2 points in space-time using Euclid's geometry, then all sorts of worrying paradoxes emerge. But as soon as you use the non-Euclidean geometries of Bolyai and Lobachevsky, the paradoxes dissolve. The geometries of these 19th century mathematicians were the key to the creation of the physics of relativity. Albert Einstein is a recognized genius, but what about the brilliant mathematicians on whose shoulders he stands? It pains me that they receive so little recognition by comparison. Seeing in 4 dimensions may sound scary, but I still remember the first time I put on those mathematical glasses of Riemann's and saw the mathematics of hyperspace. It was way, way better than seeing a movie in 3D. The mathematics of curved space and multiple dimensions is so much more than a day out at the mathematical movies. These ideas are key to navigating the structure of space and time. They're the key to Einstein's theory of relativity.
A Brief History of Mathematics was presented by Professor Marcus de Sautoy. The readers were Julian Wadham and Samuel West, and the producer was Anna Buckley.